Hello,
Good
am I
evening,
audible?
sir.
Am I audible?
Yes, sir.
Okay. Hello. Is my screen visible?
Sir.
Okay. Okay, we can start. So this is week 5 assignment solution solving session 5. So I will start with some basics, then I will solve some more problem. If you have any doubt, you can ask me. So we will start with basic concept. Uh, what is an ordinary differential equation? So have you any idea what is a differential equation? Have you studied before? Hello.
Yes, sir. I had it in my 12th, sir.
Okay. So I'll start with basic definition, then we will see some of the types of differential equations, and we'll solve how to deal with some sort of differential equation and how to solve the differential equations. There are various ways to solve the differential equations. So I'll solve few of the problems. So let's start with what is an ordinary differential equation. So as we know that when all the derivatives involves in a differential equation, these differential equation, they are called ordinary differential equations. So we can give it a example like d square y by dx square plus dy by dx plus y equal to 0. So coming to the next concept, what do we mean by a linear ordinary differential equations? So it is a subclass of all ordinary differential equations. So a differential equations is linear if it is linear in the unknown function and its derivative. So we can take it as this as a examples of linear differential equations. So here I can give another example, d square y by dx square plus dy by dx plus y equal to x. So here unknown function is y, and their derivatives is like dy by dx, d square y by dx square. So the definition for a linear ordinary differential equations, if it is linear in the unknown function and its derivative. So you can see that it's all are linear, that means they have no higher order power like d square y by dx square whole square or dy by dx whole square. There is no term like that. So what is the example of non-linear ordinary differential equations? So examples of non-linear ODE is x square d square y by dx square plus x square y equal to sine y. So you can see that there is an x square terms here. So similarly you can say that dy by dx whole square plus xy is equal to 1. You can see that there is also a non-linear terms. So this is the example of non-linear differential equations. So in general the linear differential equations has the form this one is L y of x is equal to f of x. So this is the general form of linear differential equations. So here y is the unknown function and here f of x is a known function. Or this function is sometimes called as forcing function or this function is in general this f of x is independent of y. As you can see, it's only dependent on x. So if f of x is equal to 0, then the differential equation is called homogeneous. And if f of x not equal to 0, then it's called inhomogeneous. So next we will check order of an ordinary differential equations. So let's say there is a differential equation x square dy y dx plus x square y is equal to sine x. So as you can see, this differential equation is not a linear differential equation, linear ordinary differential equations. So this differential equation is a non-linear differential equations. So you can check its order. So here the order of this differential equation is 1, because the order is defined as the highest derivative in this differential equation. So here the highest derivative you have dy by dx, that means you have done one time derivative, so the order is 1. Similarly, you can check for the differential equation uh, d square y by dx square plus dy by dx plus y is equal to 0. So here you can see that there is a second order derivative dy by dx square. So this differential equation has order 3. So you can similarly a generalized differential equations of order n can be written as a n x n. A n is a function of x, dn y by dxn plus a n minus 1 x dn minus 1 xn minus 1 up to a0 x, the function of x, and the right hand side is a function fx. Here this function is bx. So here the highest order of the differential equation is n. So next we can check the first order differential equation. We will play around first order new order differential equations. So the first we first consider the ordinary differential equations having a general form dy by dx is equal to function of x y. So this differential equations, this side, this function is unknown, so we cannot say whether this differential equation is linear or not linear. So let's see how to solve this kind of differential equations. So there is a method called separable of variables. So we will see by this method which kind of differential equation we can solve. So the differential equation as given as dy by dx is equal to minus of px over qy. So this general form of the solution of this differential equation, if you see this kind of differential equation, the solution of this differential equation can be written as this y0 to y q of y dy. So later on I will explain how to solve, but this is the standard form of this kind of differential equation and the solutions. So we can take an example of let's say the there is a radioactive sample, and the decay of radioactive sample is proportional to the remaining number of atoms. So if the rate constant, let's say rate constant is lambda, and if the number of atom at t equal to 0 is let's say n0, then we can find the number of atoms at a time t. The differential equation we can write as number of atom at a time t, that dn by dt is equal to minus lambda n. So you can solve this differential equation is very straightforward. The solution is minus lambda t, because you can take this function to this side, dn by n equal to minus lambda dt. So after that you can integrate and then you can solve. So the solution will be in this form. So coming to the next example, so let's say there is a differential equation x dy by dx is equal to y plus 1, and the you can solve this differential equation also in the same way. So this dy by dx dy by y plus 1 is equal to dx by x. You can take this y plus 1 into the denominator, and then you can integrate over dy by y plus 1 is equal to integration over this. So you can solve this integration. So coming to the next part, we'll look what is in linear first order ordinary differential equations. So the general form of this kind of differential equation is dy by dx plus p of x y is equal to q of x. So as you know, if this qx is equal to 0, then it's called homogeneous. If it's not equal to 0, then it's called inhomogeneous. So let's check for the solution for homogeneous differential equation. This one is, you can write as is equal to 0. If differential equation is homogeneous, then q of x equal to 0. So you can write dy by dx is equal to minus px y. So then you can use the variable separable method. So there is a straightforward solution. If you see this kind of differential equation, you can write that y is equal to a e power minus integration over px dx. So this is the most general solution. So later when I'll solve the problem, we'll use these expressions. So this is the general solution for differential equations. So here uh, I am stating the solution for this kind of solution differential equation directly, so you can check the notes for the details. So for inhomogeneous equation, dy by dx plus pxy is equal to q of x. If this qx is not equal to 0, this is a inhomogeneous equation. So you can solve this inhomogeneous equation. So the solution is given as y equal to exponential minus I q of x e power I dx plus c power c into e power minus I. So where I is equal to integration over p of x dx. So this is the solution for inhomogeneous linear first order differential equation. So in the problem solving part, I will explain examples. So if this c is an arbitrary constant, so this c value, if you have given any boundary condition, so you can calculate this c value. Next we'll see some of the differential equation and how and its uses. So before that, we will see what do we mean by an orthogonal trajectories. So the solution for this differential equation, you can see that they represents some family of curves. So there are sort of differential equations. So when you saw the disintegration of an atom, radioactive element, so you got the solution as y equal to, or n equal to n equal to n0 e power minus lambda t. So if you plot this differential equation, solution of this differential equation, you will get a graph, a curve like this, because as time proceed, so the radioactive number of radioactive element will decay. So the solution of these differential equations represents some family of curve. So here also this uh, family of curves. So sometimes to construct the families of curves that perpendicular to them are called the orthogonal trajectories. If there are some curves, the perpendicular to these curves are known as the orthogonal trajectory. So we will see by an example. Let's say there is a differential equation dy by dx is equal to y plus 1. So here if you solve the differential equation, the solution is a x minus 1. So here a is an arbitrary constant. If the boundary value is given, so you can calculate the a also. So here a is a free parameter. So if you want to find the orthogonal trajectory, so this represent a families of curve, because for a particular values of a you will get one curve, for particular values of another particular values of a, so you will get another curve. So So if we want to find some orthogonal trajectory to these families of curve, so we need to find first dy by dx, that is y plus 1 by x. So you can take this x here, so this y plus 1 by x. So the orthogonal trajectory have the condition dy by dx is equal to minus x by y plus 1. So if this is the original differential equation, so the orthogonal trajectory will have these conditions. These conditions. So then if you solve these differential equations, so then we will get the families of uh, families of curve like x square plus y plus 1 square is equal to c. So here you can see that this is a equation of circle. So if you solve this differential equation, you will get this as a solution. So this equation is a this equation is the equation of circle. So similarly, for other differential equation, you can find the orthogonal trajectory corresponding to the differential equations. So coming to the next part, so next is what do we mean by an exact differential equation. So exact differential equation, uh, I will state when a differential equation is said to be exact. So let's say the differential equation dy by dx is equal to f of xy. This is the function dependence on x and y is unknown here. So let's say we can write f of xy is equal to minus p of xy divided by q of xy. So we can write this differential equation as p of xy dx plus q of xy dy is equal to 0. So we need to check whether the differential equation is exact or not. So we can check that if the partial derivative of del p by del y is equal to del q by del x, then the differential equation is uh, an exact differential equations. So then so next we'll see that the solutions solutions of linear first order ordinary differential equation. So we will use some properties here. So let's say there is a differential equation dy by dx plus pxy is equal to q of x. So here you can take as this qx is not equal to 0, that means it's an inhomogeneous linear first order ordinary differential equation. So some properties of this linear first order ordinary differential equation as the solution of the inhomogeneous ordinary differential equation is unique up to n arbitrary multiple of the solution of the homogeneous ordinary differential equations. So let y1x and y2x be two solution of ordinary differential equation. That means, so initially we have the differential equation dy by dx plus px y is equal to q of x. So let's y1 and y2 are the solutions, so this will be satisfied that dy1 dx px y1 is equal to qx. Similarly dy2 dx plus px y2 is qx. So you can see that the right side of both the differential equations are same. So you can make it as a homogeneous differential equations. How? You can subtract one from another. So the dy1 by dx plus p of x y1 minus dy2 by dx plus p of x y2 is equal to 0. So then it will be d of dx of y1 minus y2 plus p of x y1 minus y2 is equal to 0. So you can see that if you substitute y1, let's say y1 minus y2 some notation as a z, so you can see that this is a linear differential homogeneous linear differential equations. So again we need to check what is linear dependence of functions. So let's say the functions f1 of x, f2 x, so fn x are linearly dependent. So from the vector space we know that if they are linearly dependent, that means some linear combinations linear combination of the of them is identically 0. That is, if there are constants, such as k1 f of 1 x plus k2 f2x plus kn f1 x is equal to 0. So if the functions f1x, f2x, f of nx have derivatives of order n minus 1, and if, let's say, w is equal to determinant of f1x, f2x, f of nx and their derivatives up to f of n minus 1 x, f2n minus 1 x up to fn n minus 1 x is not equal to 0, then the functions are linearly independent. So this determinant is known as Wronskian, WRONSKI. So next we will see a special kind of differential equation, although we will not solve it here. So this differential equation is known as the Bernoulli equation. So this differential equation has the form dx dy by dx plus p of x y is equal to qn of x y to the power n. So next we will see what is an homogeneous equation. So before that we will see homogeneous functions. So a function is homogeneous with degree n if it can be written as x to the power n f of y by x. So we can see an example that x square minus 5 of xy plus y cube by x, and another example is x to the power minus 1 into y4 minus x cube y minus xy square of sine x by y. So not homogeneous, so we can see an example that which are not homogeneous. So x square plus y and x plus cos y, another one is x so how to solve this if there is an homogeneous differential equation? So in the problem session we will see. So next we will see what is an ordinary differential equation of constant coefficients, then we will solve some of the problems. So coming to the next, we mean by the second order homogeneous linear equations with constant coefficients. So we'll see that how this kind of differential equation looks like. So the general form of this kind of differential equation is, let's say, a2 d square y by dx square plus a1 dy by dx plus a0y is equal to 0. So you can see that this is a linear equation. First you can see that there is no squared terms, so it's a second order. You can see that the highest order derivative of this differential equation is 2, second order, and constant coefficient. So your a2 a1 a0 ai I 0 to 2 are all are constants. So there are also linear differential equations which have variable coefficients. That means a2 is some function of x, a1 will be some function of x, a0 will be some function of x. So these are not differential equation of the constant coefficients. So we'll see an example, then how we will write the auxiliary equation for this differential equations, then we can solve this differential equation. So given a differential equation, let's say d square y by dx square plus 5 dy by dx plus 4 y is equal to 0. So here you can check that here the a2 is 1, a1 is 5 and a0 is 4. So you can write this differential equation as in a auxiliary equations. Auxiliary means you can write d is equal to d as d by dx. So here d square means d square by dx square. So this differential equation you can write as d square plus 5d plus 4 into y is equal to 0. That means this is a operator kind of things. So this operator is acting on y. That means here the operator is d is equal to differential operator dx. D square is d square by dx square. So this differential equation here, this is the auxiliary equation of this differential equation. So similarly for other if other differential equation also you can write as it is. So the we will solve this kind of differential equation. So let's say this differential equation, let's take an example of differential equation. Let's say if the auxiliary equations are given, that means d for d plus 1 y is equal to 0. If this is an auxiliary equation similar to this, so uh, this differential equation you can see that d plus 4 y is equal to 0 and d plus 1 is equal to 0. So here if you solve this is a fine first order differential equation, like d by dx plus 4 dy by dx plus 4 equal to 0, and this one is also dy by dx plus 1 y plus 4y is equal to 0. So you know how to solve this kind of differential equation. So if you solve, so this auxiliary equation reduced to this form, so you can separate it out this in these terms. So these are two first order linear differential equations. So you know the solution of the first order differential equations, how to solve them. So let's say to dy by dx plus y is equal to 0. So you can say that dy by dx is equal to minus y. So you can solve dy by y is equal to minus dx. So similarly you can solve d plus 4y is equal to 0. So the final solution will be the linear combination of these two solutions, because our original differential equation was a second order differential equation. So you, by using the auxiliary equation, you reduce to two linear differential equation first in first order. So the final solution will be the linear combination of, so let's say the final first from the first equation. So this has a solution, let's say y equal to some constant e power minus 4x, and this has a solution y equal to c2 e power minus x. So if you integrate then you will get this exponential minus x. So the solution will be the linear combination of both two solutions, c1 e power 4 minus 4x plus c2 e to the power minus x. So similarly you can check for other same kind of differential equations also. So we'll look another kind of differential equation, which is d square y by dx square plus p of x dy by dx plus q of x y equal to 0. So you can see that these are not constant, this is the function of x. So here there is no you cannot find the general solution like the constant coefficients. So in the problem solving session I will show how to solve this kind of differential equations. So I will state some of the properties of this kind of differential equations. Let's say the differential equations is a2 d square y by dx square plus a1 dy by dx plus a0y is equal to 0. So in the previously we saw that we need to find the auxiliary equations corresponding to these differential equations to solve this differential equation. So this is the auxiliary differential equation, auxiliary equation for this differential equation. So after that we need to reduce this equation into two linear first order equations. Then we have to find the solution for let's say y1 is c1 and some function of x, and y2 is c2 some function of x. So the final solution was the linear combination of this y1 and y2. Let's say this is g of x plus c2 g of x. So apart from this technique, so there is another technique. Let's say suppose we will assume y is equal to e to the power mx. So let's say d square y by d square by dx square is m square, d by dx is m. So similar to this we can write as this equation a2m square plus a1m plus a0, and we took y as e power mx, so in the place of y we will put e power mx is equal to 0. Since this e power mx cannot be 0, the a2mc square plus a1m plus a0 will be equal to 0. So here uh, if uh, uh, let's say this is a second order linear equations, so if we found that this, that means if you solve this equation we will get two values of m, that is m1 and m2. So if m1 and m2 are two distinct roots, so then the solution will be y equal to a e power m1x plus b e power m2x. If the m1 and m2 are two distinct root, then you will get the solution as y is equal to e power m1x and m2x. So let's say if m1 m2 are complex conjugate roots, that means m1 and m2 is equal to a plus or minus ib, then the solution will be y equal to e power ax a cos bx plus b sine bx. So similarly there is another possibility also. uh, so if m1 is equal to m2 and that is equal to minus a1 by 2a2, then the solution is y1x is equal to e power minus a1x by 2a2. And similarly uh, the general solution for this equation will be y(ax) plus b e power minus a1x by 2a2. So we'll see example now. So given that uh, mark all the ordinary differential equations that are linears. So we can see that here the option number A is option number B, option D, and option C and option D. So linear differential equation means in general L y x is f of x. So here from the vector space you know that what is a linear operator, so same concept you will apply here. So this is the generalized form of a linear differential equation, and it has a property like here y is unknown function and f is a known function independent of y. So here L is a linear operator that converts y into another function. That function is f of x. So you can say like that. So since L is a linear operator, so L acting on a y1x plus b y2x will be equal to a L y1x plus b L y2x. So you can check from the first let's check the first option, x d square y by dx square. If they satisfy the above equations, dy by dx plus sine x. So here the differential operator L is equal to x d square y dx by dx square minus d by dx, and here f of x is equal to sine x. So you can write this as L of y of x is equal to sine of x. So here the linear differential operator is this. So let's check L of a y1 plus b y2 is equal to x d square a y1 plus b y2 by dx square minus derivative of ay1 plus by2 by dx. So next you can see that a, you can, this, as this a is a constant, so you can pull it out. Ax d square y1 by dx square plus b x d square y1 by dx square minus a dy1 by dx minus d b dy2 by dx. So here you can rearrange this. So as a is equal to x d square y1 by dx square minus dy1 by dx. So you can bring to this side plus b x d square y2 by dx square minus dy2 by dx. So you can see that this is a linear operator let on y1, this is also a linear operator on y2. So here you can see that l y1 plus b l y2. So it satisfied the following for. So the option a is a correct option, which is the ordinary differential equation and it's linear. So similarly, we'll check for the option b. Let's check whether it's in linear ordinary differential equation or not. So the option b is given as, the option b is, let's say, x d square y by dx square now equal to dy by dx plus dy by dx is given. So you can say it by inspection also, because there is a non-linear term is x cube, but for this is not the sufficient condition to check whether this differential equation is linear or not. So sometimes it seems easy to look out that there is a non-linear term or higher order term, but this above condition you need to check all the times, so that you will not make any mistakes. Sometimes it's look like there is, this is a non-linear, but it may be a linear equation. So the sufficient conditions to check the linearity of a differential equation is as we check in the option number a. So similarly for option number b also you can check. Let's say L of y is equal to x square d square y by dx square minus dy by dx minus dy by dx cube equal to 0. So if you apply a y1 plus b y2, so you will see that will be equal to, x d square a y1 plus b y2 divided dx square minus d of a y1 plus b y2 by dx minus d of a y1 plus b y2 by dx whole cube. So that is equal to ax d square y1 by dx square minus dy1 by dx plus b. You can expand these terms and check. That will be x d square y2 by dx square minus dy2 by dx minus a dy1 by dx plus b dy2 by dx whole cube. So if you expand this, you will not get L of a y1 plus b y2 not equal to L y1 plus b L y2, just because of this cubic term is there. So here option B and option C is not in option B is not a linear ordinary differential equation. Similarly, this is not in the form of an ordinary linear differential equations, because if you can see that L of y of x is equal to f of x. So here if you write this equation in this form, so you'll get y, you will get that d square y by dx square is equal to minus dy by dx is equal to sin y by y. So this is L some function of y x equal to, this is not in the form of f of x, this is in the form of f of y. So this is not a linear ordinary differential equation. So similarly you can see this also. So here the option A only represents the linear ordinary differential equation. So answer is option A. So all other options are not. So coming to the next problem, so there is mark the ordinary differential equations that are second order. So the order of the differential equation depends on the highest derivative present in the differential equations. So here the highest derivative with non-zero coefficients in a differential equations decides the order of the differential equations. Here you can check that here the order is 2, here also the highest derivative is 2, here also it's not mentioned whether it's linear or not. So all the options are here represents the ordinary differential equation of the second order. So the options all options are correct. So coming to the next problem, find the orthogonal trajectory of the family of curve represented by x is equal to y plus 1 plus c e power y. So to find the orthogonal trajectory, so here in general in the concept session we saw that y is represented as some function of x. Here there is the other way around, that x is represented in function of y. So you can consider that y and x are a dummy variable, so you can interchange it. So similarly here we'll explain, we'll find the dx by dy, so that will be, if you derivative once, 1 plus c e to the power y, and derivative of y equal to 1, derivative of 1 equal to 0, and this will be the derivative of exponential y will be the same. So then you can see that here in this equation you can find that x minus y is equal to 1 plus e power c e power y. So you can check that 1 plus c e power y is equal to x minus y. So you can substitute dx by dy is equal to x minus y. So as you know that the slope of a family of curve is always represented as dy by dx. So here the slope is dy by dx. Let's say its slope is n, will be 1 by x minus y. So for the orthogonal trajectory, so this dy by dx should equal to minus 1 by n. So in the example we saw that if dy by dx is x plus y, then for the orthogonal trajectory dy by dx will be 1 by x plus y, just for a convenience. So here also you can apply same thing. So dy by dx equal to minus 1 by m, which will be equal to y minus x. So dy by dx is equal to y minus x. So you can write that dy by dx minus y is equal to minus x. So this dy by dx minus y is equal to minus x is in the form dy by dx plus p of x y is equal to q of x. So this is a linear first order inhomogeneous differential equation. So here p is equal to minus 1 and q of x equal to minus x. So to solve these differential equations, we know that is given by solution is given by y equal to some constant e power p to the power x dx. So this is an homogeneous differential equation. You know the solution as that it's mentioned before. this is the solution for the inhomogeneous differential equation. So you can put this directly there and you can find the solution. Y is equal to so if you solve this problem using this formula, so you will get that y is equal to x plus 1 plus c1 e power x. So the option which is correct is equal to option C is coming to the next part. So identify all the differential equations that are exact. So you might be confused that this is not in the differential equation form, like L of y is equal to f of x. So you can convert this equation into differential equations, like let's say it's given 3x plus 2y dx plus 2x plus y dy is equal to 0. So this is in the form of p of x y dx plus q of x y dy is equal to 0. So if this differential equation to be exact, so you need to check the conditions as dp by del p by del y is equal to del q by del x. So this partial derivative with respect to y of p is should be equal to partial derivative of q with respect to x. So here in the first option, the p of x y is equal to 3x plus 2y and q of x y is equal to 2x plus y. So you can check that del p by del y is equal to 2 and del q by del x equal to 2. So you can check that del p by del x del y is equal to del q by del x. So the first option A differential equation is exact. Similarly for option B is given y square plus 3y dx plus 2xy minus 4 dy is equal to 0. So you can check that p of x y dx plus q of x y dy is 0. This is in the form. So here p of x y is equal to y square plus 3y and q of x y is equal to 2xy minus 4. So if you find the partial derivative of p with respect to y, you will get 2y plus 3, and partial derivative of q with respect to x is equal to 2y. So here del p by del y is not equal to del q by del x. So option B is not an exact differential equation. So similarly for C also you can check. For C you will get del P by del Y will be equal to del Q by del X, and uh, you will not get. And for D you will get del P by del Y is equal to del Q by del X. So in similar way you can check, and the options are A and D are correct. So question number 5, solve the following differential equation by separating variable if the boundary conditions are given. X y at x equal to 1 is equal to e, and we have to compute y at x equal to 10. So let's say the differential equation x dy by dx minus xy is equal to y. So x dy by dx, so you can bring this y, or you can take this one into right side, that will be y plus xy. So that will be x dy by dx is equal to y 1 plus x. So you can do that dy by y is equal to 1 plus x by x dx. So this is a very straightforward equation, derivative differential equation. So you can get integrating both side, so you will get dy by dx, sorry, dy by y will be equal to 1 by x dx plus 1 dx. So you can simply write 1 by x plus 1 dx dy by y. So if you perform the integration, you will get ln y is equal to ln x plus x plus c1. So here integration of 1 by y with respect to y is ln y, and 1 by x is x ln x. So you can do one thing, that ln x plus, you can write ln x equal to ln e power x plus, let's say this c1 is a constant, so you can write it as ln c1. So this whole total things will be c of x e power x. So ln a plus ln b is equal to ln a b. So you can write these properties. So next we have given y at x equal to 1 is e. So you can write as c x1 e power 1 is e. That means c equal to 1. So here given at, because if both are given ln y equal to ln c, ln y equal to ln c x e power x, that means y equal to c x e power x, and it's given y at x equal to 1 is e. So that means you can put e here, then c and x is equal to 1 and e power x is also e. So here you will get c equal to 1. So what is the general solution for y of x is equal to x? You got the value of c as 1 and for e power x, this is the general solution of y. So next we have to compute y at x equal to 10. So you can just substitute 10 in the place of x, so that will be e power 10. So the option B is correct. So here there is a typo, that will be 10. So this condition is given as a boundary conditions. So if the boundary condition is given, so you can find this arbitrary constant c1. So next, solve the following differential equation dy by dx. Given the initial conditions, we wish to compute y at x equal to y1 is y1, the root of which the following equations represent y1. So given differential equation dy by dx is x plus y plus 4, x plus y minus 6. So here we can substitute as z is equal to x plus y minus 6. So then we can get x plus y is equal to z plus 6. So this technique, will using this technique to reduce this kind of differential equation, this d. So then in the place of, you can get z equal to x plus y minus 6, and here we will get x plus y equal to z plus 6. So you can differentiate with respect to x these equations, so you will get dz by dx, then it will get 1 plus dy by dx. So this will leads to dy by dx is equal to dz by dx minus 1. So in the place of dy by dx, you can substitute this dz by dx minus 1. So after substitution, you can check that this equation will be dz by dx minus 1 will be z plus 10 by z. So here, you can see that this is a form of differential equation. You can do the variable separable method, so you can see that this is a dz of dz by dx, and this side is only a function of z. So here you can bring this function to this side. So let's say dz by dx equal to z plus 10 by z plus 1. So then if you solve these differential equations, let's say this dz by dx minus 1 equal to z plus 10 by z, and dz by dx equal to z plus 10 z minus 1. So this is a total function of x. You can get at this function dz divided by z plus 10 by 2 minus 1 is equal to dx. Then you will get, if you integrate over both sides, then writing the direct solution, you will get ln z plus 5 equal to z minus 2x plus c. So then you can substitute z is equal to x plus y, and you will get, you can substitute as the previous substitution, z equal to x plus y minus 6, x plus y minus 6. So after substitution you can apply the boundary condition that y it x equal to 0 is equal to 2, it x equal to 0 to 2, and you will get the c1 will be minus 2. So again, substituting the value of c1, you will get ln 5 ln x plus y minus 1 is equal to y minus x minus 2. So this is the solution of given first order ordinary differential equation. Now you can substitute y at x equal to 1 is y1. So in this equation you can substitute this 5 ln 1 plus y1 minus 1 is equal to y1 minus 1 minus 2. So if you solve these equations, then you will get ln y1 5 is y1 minus 3. So I'm directly writing the answer, so you can check, it's a little bit algebra. So the option B is the option B is correct. Coming to the next problem, it's given d square y by dx square plus 8 dy by dx plus 15y is equal to 0. So you can check that this is a second order linear ordinary differential equation with constant coefficient. So we can write, we previously we know there we can do two types of method to solve this equation. One is the auxiliary methods, like where d is d square y by d by dx square. So this equation can be reduced to d square plus 8d plus 15 y equal to 0, and you can solve this, you can reduce this second order into two first order equations, then you can get the solution which y1 y2, and the final solution will be linear combination of y1 plus y2. And another method was y equal to e power mx. So you will get differential equations with m square plus 8m plus 15 e power mx is equal to 0. As you know, this is not 0, so you will get m value is m1 and m2. So if two values are distinct, we know the solution. If two values are complex conjugate to each other, then we know the solutions, and if two values are equal, m1 and m2 are equal, then we know the solution. So here we check, I told the procedure. I'll skip bit of the steps, so you can do it. So here let's say the auxiliary equation is d square plus 8d plus 15 is y is equal to 0. So if you solve this equation, then you will get the value of d as minus 3 and minus d as minus 3 and minus 5. That means you will get d plus 3y and d plus 5y equal to 0. So in so is this, or in terms of like y equal to e power mx, so let's say we took y equal to e power mx. So this, in place of t you can so we will put y equal to e power mx. So here in the place you can write it as m square plus 8m plus 15 for mx equal to 0. So if you put this equation into the original differential equation, you can get this equation. So here if you solve this equation, that this is not equal to 0, that means m square plus 8m plus 15 is equal to 0, you will get the m value is equal to minus 3 and minus 5. So here you got the two distinct roots. If there are two distinct roots, so the solution will be y equal to a power e m1x plus b m2x. Here m1 is minus 3 or m2 is minus 5. or you can take other way around. So y equal to a e power minus 3x plus b e power minus 5x. So then what is given? So given the initial conditions, y at x equal to 0 is 2. So we'll check that y prime at x equal to also given. So y prime will be minus 3 a, the first derivative of y is minus e power minus 3x minus 5b e power minus 5x. So it's given y at x equal to 0. If you put at x equal to 0, so y will be a plus b equal to 2. It's given y at x equal to 0 is 2. So you'll get one equation, let's say equation number 1. So another condition is given y at x, y prime at x equal to 0. That will be, if you put x equal to 0 here, so you'll get minus 3a minus 5b, and it's given at y equal to y prime at x equal to 0 is minus 8. So you'll get minus 8. So let's say this is equation number 2. So if you solve these two equation number 1 and 2, so you will get a is equal to b equal to 1. So hence, so the solution was a e power minus 3x plus b e power minus 5x. So you can put a and b equal to 1, so its solution will be a power 3x plus e power minus 5x. So next we have to find y is x equal to 1. So here if you put x equal to 1, then y will be 1 by e power 3 plus 1 by e power 5. So let's check which which option is correct. See here, option A is correct. So there are two methods. You can choose either of the method, you will get the same answer. So the next question is, mark all the statements that are true. The x square minus 4xy plus 3y4 by x square is a homogeneous function of degree 2, and the second one is x square minus y square minus y power 4 by x minus 3x square y cos x by y is a homogeneous function of degree 3, and the option C and option D are given as it is. So we have to check. So let's say a real valued function of two variables x and y is a homogeneous function if it satisfies the condition f of alpha x alpha y alpha to the power k f of x y. So here k is some constant and all are all real numbers alpha. So the k is called degree of homogeneity. So let then their given statements are, let's say f of x y is equal to x square minus 4xy plus 3y4 by x square. So we can check f of alpha x alpha y is equal to alpha square x square minus 4 alpha square x square. We can substitute alpha x and alpha y in the place of x and y, so will be equal to 3 alpha square y fourth by x square. So next we can see that this, if we are taking common alpha square, that will be equal to alpha square x square minus 4xy plus 3y fourth by x square, which is alpha square of x y. So you just see that the k represents degree of homogeneity. So here k is 2, so you can say that f of 1xy is a homogeneous function of degree 2. So similarly for b, you can check b is given as x square y square minus y to the power 4 by x minus 3x square y cos x by y. So similarly you can do f2 alpha x alpha y, so you will get f of alpha x alpha y is equal to alpha to the power 3 f2 xy. So here is a degree homogeneous function of degree 3. Similarly for c also you will get f2 alpha x alpha y is equal to alpha to the power 4 f of 3 xy, so it's a degree 4. So here you can check that option D is the functions are not homogeneous functions. Likewise for the option number A, B, C. So here the all the options are correct. So coming to the next part, so it's given that d is equal to d by dx be the differential operator. Mark all the statements that are true. So let's check one by one. So the action of an operator can be known only when it is operated on a function. So here you can see that it's only a differential operator, but they are not acting upon any function. So to check the differential operator, we need to apply this differential operator on a functions. Let's say d of plus x y, we acted upon the y, that will be d by dx plus x y. So then you can see that dx upon d by dx plus xy, so this is equal to d square y by dx square plus x dy by dx plus 1. So you can write it as equal to d square y plus x dy plus y. For the second option, you can check d plus 1, d square minus d plus 1 y is equal to, so I omitted a step, that will be equal to d, if dy dx acting upon dy by dx, that will be dy by dx square, plus if this is acting on xy, then it will be, first let's say x dy by dx plus y into dx by dx. So dx by dx equal to 1, this one is 1, so you'll get d square y plus x dy plus 1 equal to. So here that means d acting upon d plus x is equal to d square plus xt plus 1. So option A is correct. Similarly, you can check for the rest of the options. So I am leaving it up to you. So the another statement is correct is option B is also correct. You can check. So coming to the next problem and the last problem. So here it's given by inspection guess one solution for differential equation of x square d square y by dx square plus x dy by dx minus y equal to 0. So as you know, there is not a exact solution of this kind of differential equation, because these are the differential equations but not having the constant coefficients. So we know the differential solution for the constant coefficients. So the boundary conditions are given, y is equal to x equal to 1 equal to 2, and y at x equal to 2 is equal to pi by 3. We have to compute y at x equal to 3. So this kind of equations, by let's say we just guess a solution as y1 is equal to x. So So we want to find the second solution. Just because it's a second order differential equation, there will exist two solutions. So let's say second solution is y2x is equal to y1x v of x, that is x v of x. So thus dy2x by dx, if you derivative of this, then dv by dx plus vx. If you differentiate this, so again if you do the second derivative, d square y by dx square y 2x will be equal to x d square bx by dx square plus 2 dvx. This 2 factor comes due to, if you do the derivative of this term, there you will get extra dv by dx term, so this term will add up. So then you can substitute this, then you can substitute this expression into the original expression as, let's say, x square d square x d square v by dx square plus 2 dv by dx plus x into dv x by dx plus v of x minus, in the place of y you can write as x vx is equal to 0. So then if you do a little bit algebra, then you will get x cube d square v of x by dx square plus 3x square del v of x by dx is equal to 0. So then if you taking the x square common, so you'll get del square vx by del x square is equal to minus 3 by x del v of x by dx. So let's say now we will assume omega x is dv by dx. So this term will be again d omega by dx is equal to minus 3 dx by x. So you can, this is a straightforward equation, you can integrate both sides, then you will get ln omega is equal to minus 3 ln x. Let's say the arbitrary constant is in the form ln c1. So this constant we just take arbitrarily by seeing the form of the actual solutions. So here you can find omega as c1 by x cube, because these are two ln. So if you multiply ln omega is equal to ln a minus b equal to ln a minus ln b equal to ln c1 by x cube, that will be equal to ln So omega will be equal to c1 by x sq. So next you can do is, you got the omega as c1 by x sq. So as you know, omega is dv by dx, so you'll get c1 by x sq. So similarly you can find here also v of x is equal to, if you take dx into this side, so you'll get c1 by x sq dvx integration dx. So you'll get v of x is equal to minus c1 by 2x square plus c2. You just simply integrate this. So next what you can do is, we got that vx, the form of vx we got. So as you know, y2 is equal to x vx, so you can substitute there, that's c1 by 2x plus c2x. So the most general solution is, so first you take the solution by inspection, y1 is equal to x, then you put y2 is equal to x bx. So as I said, there is no particular generalized solution for this kind of differential equation, so you need to do this kind of procedures. So here y of x, you got minus c1 by 2x plus c2x. So the given boundary condition that y1, y at x equal to 1 is minus c1 by 2 plus c2 is equal to 2, y at x equal to 2 is minus c1 by 4 plus c2 is 5 by 2. It was given. So by solving this equation 1 and 2, you will get c1 equal to minus 2 and c2 equal to 1. So therefore one particular solution will be 1 by x plus x, putting c1 and c2, and then you will get y at x equal to 3. You just simply put the values of c1 and c2 here, you will get the y 1 by x plus x, and you will put at y at x equal to 3, so you'll get 1 by 3 plus 3, that is 10 by 3. So here the solution, the options number B is correct. So if you have any doubt, you can ask. Hello.
Yes, sir. No doubt, sir.
Okay.